Yeah, we have two more classes left. So we'll talk about some continuous inverter-based amplifier. We'll talk about some inverter-based fully differential amplifier. We'll talk about another version of a differential circuit and inverter-based switch capacitor filter. That's it. Okay. Yeah. So we talked about the nota cell before, right? Let's continue with the nota cell. This nota cell is a differential amplifier, fully differential amplifier, using inverters. Okay. So, this is input. Yeah, the nota cell is fully differential amplifier. I may have a large inverter, VIP, and then VIM, and then I have a small inverter, and then I have some bias point, logic threshold inverter. Yeah, this is a VOM, VOP, okay? So those two inverters determine common mode output voltage, okay? They determine common mode output. Common mode VR. Right. So here's we put 3.3 volt for all those inverters. For these two cross-coupled inverter, we used different values. Okay. We may use different values. Yeah, for the small signal equivalent circuit, let's just see. Oh yeah, I don't have space. I need some space here. Yeah. Oops. Let's look at the small signal equivalent circuit of a nota cell. Okay. Yeah. Let's start with the cross-coupled inverter. Yeah, I have a cross-coupled inverter. What is the impedance between these two nodes? See, this is V1, and then let's just see, this is V2, and then we'll have some small signal current flowing in and flowing out, okay, the same current. Yeah, this voltage is V1 to ground, right? This is V2 to ground. So then we can convert this inverter, the upper inverter, by this GM V1. May have a R1 there, R1. Some arrow. Yeah, actually this is V2 to ground, right? Yeah, so I have this is V2 to ground. So how about this lower inverter? Yeah, similarly, it has GMV2, right? GMV2, and then arrow. So this is my V1 here. So I want to calculate current going in and going out, right? They should be the same. Then, see, applying KCL there, my current I, KCL at this node. That's GMV2 plus ROV2, right? V1. This current is V1 divided by RO. I want to calculate, apply KCL there. What's I? Yeah, my I equal minus GMV1 minus ROV2. Okay. Yeah, they should be the same, right? Because of KCL. This equation must be same as that equation. Then we can find the relation between V1 and the V2. Then, yeah, they should be the same. Okay. Then, how come this is, there is a, let's just see. It is correct. Yeah, I is going in. So this current is flows in V2, GMV1. Okay, that's fine. Okay, let's just see. This is GMV1 plus V2, right? Oh, how come? So GMV1 plus V2 RO V1 plus V2 equal 0. What does it mean? Oh yeah, it means V1 plus V2 equals 0. Okay? So it should be differential. It means, say for example, say if this is half of VID, then this should be minus half of VID in this structure. Okay? Then I can calculate my I by applying this minus half of VID, half of VID there. Okay? So my current I equal just minus GM half of VID plus RO half of VID. So VID of I, that's my impedance, is VID of I equal just 2 minus GM plus 1 over RO. Okay. So my impedance looking between those two nodes is this one. Okay. If I neglect this RO term, it should be just minus 2 over GM. Okay. Negative. The impedance looking across cross-coupled inverter is minus 2 over GM. Question.
저 스몰 시간을 썼을 때 그 인버터의 n모스랑 p모스 그러니까 각각 하나씩만 지금 제 생각이 있는 것 같은데 예를 들어서 인버터에는 저 GM이 두 개가 있지 않습니까? p모스 쪽, n모스 쪽 왜 한쪽만 그러시나요?
Okay. The question is each inverter has nMOS and pMOS, right? Let's see. They are adding together. So, you know, I have an inverter VI, and then this inverter is VDD 0, and this is VO. This is VI, right? So actually they are adding together. So yeah, as you stated correctly, this is GMNVI and GMPVI in the same direction. GMPVI, right? So I have some RO. This RO is also RON parallel ROP. So this is my VO node, right? So my GM is actually, GM of inverter is actually GM of nMOS plus GM of pMOS at the operating point, okay? So no problem, right? Just one GM. Question? Okay. Then let's continue with this inverter with the input and output connected. Yeah, what's the impedance of this one? What's impedance? Yeah, you can easily find see, this is a V1. My output is also V1, right? So equivalent circuit is just GM V1 and RO. This VO is connected to VI, right? So like that. So what's the current here? So my Rin equal just V1 divided by I, right? So my current is just V1 GM V1 plus 1 over RO V1, right? So this is only GM plus 1 over RO, right? That's only parallel connection of those two. Close to 1 over GM. Okay? Yeah, then we can complete a small signal equivalent circuit of a nota cell. Nota cell, let's see, you can see I have GM. This is some driving transistor inverter, driving transistor VIP, and then see I have another one, right? GMD DIM, okay, and then I may have RO driver. So you can see I have that GM thing there, right? Of this inverter. That thing is just 1 over GM. GM2, maybe GM2. It may have some RO there, right? RO2. And then, yeah, this is this is 1 over GM2. Same thing is attached there, right? And then between those two, we have some resistance. That's what is that? Minus 2 over GM, negative resistance, right? I think it's a parallel, right? There is some parallel of, is this parallel? This is GM3, cross-coupled inverter. This one is 2 RO3, something like that. Was it parallel? Is this correct? Parallel. Let's just see. Parallel. Oh yeah, they are parallel. Okay, they are parallel. There is equation. Yeah, here. So it is parallel. Yeah, this should be a small signal equivalent circuit of a nota cell. Okay. Yeah, question. No? Then we can calculate the small signal voltage gain, right? For the differential mode and also common mode. Okay. Well, actually, for this one, this is for differential mode actually. For the common mode, it will work in a different way. See, let's just see. Yeah, for the cross-coupled inverter, oops. Yeah, my inverter looks like that. Yeah, for this one, see, if I have a differential mode voltage applied, then my current is that one, right? My current is just VID divided by that 2 over GM. Is this 2 over GM? GM over 2 minus GM over 2. in parallel, right? It should be in parallel. I equal parallel. I think VID over 2RO. This is 3, right? Yeah, this is for differential mode, right? How about the common mode? Yeah, this should be differential mode. So for the differential mode, the input impedance is minus 2 over GM3 in parallel with 2RO3, right? That's the differential mode impedance, right? Differential mode. Yeah, how about the common mode? Common mode. So let's try common mode. Right? For the common mode input. So for the common mode input, let's see. I will apply same current there, right? Same current, same voltage. Yeah, VIC. What should be my common mode current? This is my differential mode current, right? My differential mode current. What do you think? Is this 0? Yeah, let's try that small signal equivalent circuit again. So here's for this node. For this node, this thing has. This is node 1. For node 1, my output is. This is my IC. My output is GM3 VIC, right? Then I have RO3. Yeah, that's node 1. How about the node 2? Node 2 has a similar, right? Node 2 has, I have IC goes out, and then I have GM3 VIC RO3. Okay, this is node 2. Yeah, so this voltage is a VIC, right? VIC, both of them. Then my IC is only GM3 VIC plus VIC over RO3. Okay, I think same thing here, right? Is it same thing? No, not same thing. This one is minus IC equal for this node GM3 VIC plus VIC over RO3, right? So if I add them together, it should be 0, right? If I add two equations, they should be 0. So I have 2 GM3 plus 2 of RO3 VIC equals 0. Oh, very weird. My VIC should be 0. Okay. Then my IC should be 0. Very, very weird result. So for the cross-coupled inverter does not support the common mode input. Okay, they will cancel out the common mode component. So we don't consider common mode. I think this is open circuit for common mode signal. Okay, question. Nope. Okay, for the differential mode, we wanna, So for the differential mode, see, my VIP equal half VID. My VIM equal minus half VID. Okay. Then what's my VOP and the VOM? Yeah, they should be symmetric. So this may be half VOD. This should be minus half VOD. We can expect symmetry. Okay. Yeah, see, those are the only driving current, right? And then what's the resistance between this node and that node? So eliminate current sources, then you can see, yeah, this impedance, yeah, see, I can redraw this part, say something like, this current is the same as that current, right? if you substitute VIP, VIM there, that one differential current is flowing in, flowing out, right? Okay. So they are flowing through impedance between those two nodes, right? Impedance those two nodes, this is 2 ROD, it becomes 2 ROD, right? This node goes to ground, and then this ground goes to that node. So this is a series connection of ROD, 2 RODs, right? So, see, this is the same as, let's just say, I have ID flows into node number 1, ID flows out into node number 2, and I have a parallel connection, just series connection of 2 RD driver. Now those two things, GM2 is, 2 of GM2 is there. And then what else? 2RO2 is also there. 2RO2. And then how about that one? That's already in differential format. This thing is minus 2 over GM3. So this thing is minus 2RO3, right? So my impedance between R1, 2 is just all parallel connection, right? So 2 over GM2, this is, parallel, minus 2 over GM3, parallel, 2RO driver, parallel, 2RO2, 2RO3, okay? See, I can rewrite this thing by calculating all the conductance here, right? So, the parallel things, they add in conductance values, okay? So let's just see. We can rewrite the RID. I need more space, huh? Okay. So my Ri2 equal, say, half GM2 minus half GM3 plus 2 RO driver, 2 RO2 and 2 RO3, right? So those GM things can be dominant, right? If I make a cancel them each other, they remain there, right? So my voltage gain, which is VOD divided by VID should be, just ID, right? ID is GM driver times Ri2. Is this correct? This is a HEP, right? HEP thing, I think HEP. This right? BOD. No? So my BOD is, this is HEP. I think this is a HEP of them. So the gain is, let's see. HEP means, just GMD, GM2, GM3, those twos will eliminated, right? All those things, ROD, parallel, RO2, RO3, inverted. This will be my voltage gain. I think there should be some negative. Question. This is my differential voltage gain. So if I match GM2 and GM3 together, I mean this if this is a 0, I have a pretty large voltage gain, right? Even if I make a GM3 even larger than GM2, then sometimes I can make this thing to be 0, the entire thing, right? then I have infinite gain, theoretically. So we can try change this VDD prime value. Those GM things are related to this supply voltage, right? Because if I have my supply voltage, this is I, is this input? Current looks like that, right? Current looks like that. If I increase my supply voltage, current will look like that, right? So current increases, my GM increases with the VDD. Okay? So I can increase my GM3. For the common mode gain will be like that. For the common mode gain, this does not have any effect. So my common mode gain is GMD, GM2 plus those resistance. Okay. This is my common mode gain. So I have a common mode gain is not zero. That's no good, right? I have a pretty large common mode gain. But differential mode gain is even larger if I adjust the GM3 properly. Okay? Question? Nope.